Thirst is an important part of homeostasis, allostasis, and internal regulation. Our bodies are mostly water. We're 70% approximately in the mammalian groups. So water in the body has to be maintained within a set point range, and we need it in our circulatory system. We need it in the blood. And the concentration of water in comparison to solutes can have effects on almost any physiological process. So how do we regulate water? It can be conserved by excreting concentrated urine. So signals can be sent from an antidiuretic hormone to the kidneys to get them to produce more concentrated urine, to pull water out of the urine instead of releasing that water that we need, and also decreasing sweat. It's dangerous though, because sweat is important for us to maintain our body temperature, but under situations where we have metabolic threat, sweat may be decreased. But often what we do is we just drink more water than we need, and we excrete the rest in our urine, right? So vasopressin is a hormone in the body released by the pituitary gland in the posterior portion, and that can have downstream effects on how the body regulates water. So it raises the blood pressure, our blood vessels constrict, and it compensates for the decreased volume of water that's in the blood. Because if you leave that vasculature where it's at and you have less running through there, you can start to get damage to vasculature walls, to membranes, all kinds of things. So we're constricting blood vessels to compensate for the decreased amount of volume that's in the blood. And vasopressin is known as this antidiuretic hormone, meaning that the kidneys will reabsorb that more water and then excrete highly concentrated urine, or more concentrated urine. We have two kinds of thirst for homeostatic regulation. Osmotic thirst from eating salty foods, like this cup of noodles I'm having right here has more than 1,000 milligrams of sodium in it, which is probably at this time just wreaking absolute havoc on my body. But anyway, we also have hypovolemic thirst. This is a thirst resulting from loss of fluids due to bleeding or sweating. If people are shot, for example, and they're losing a lot of blood, oftentimes they'll be really, really thirsty when they get to the hospital, because intaking fluid can actually create a pressure that's similar. It's not going to save their life, but it's good for them. So let's talk about osmotic pressure, right? So we have solutes inside and outside the cell, and we have a membrane that separates the intracellular and extracellular space. That membrane is semi-permeable. It's semi-permeable because it doesn't allow everything to cross back and forth, right? So water can flow across that membrane, but solutes cannot. But oftentimes what happens is water flows in a concentration gradient, from low concentration to high concentration. Imagine that I've got a fish tank. The fish tank's got a barrier in the middle, right? What happens when I put full water on one side and no water on the other side, and then I remove that barrier? The water flows from the highest side to the lowest side to reach equilibrium, right? So we see the same thing with these semi-permeable membranes. And so we have solutes that are more concentrated extracellularly, for example, than on the inside. Well, the solutes can't flow from the outside to the inside to make things equal, right? So what can we do? We can push more water from the inside to the outside. When we do that, the concentration of water to solute is the same intracellularly and extracellularly, and then the cell actually shrinks because it has less water in it. It's a really neat process. So look at this. On the left side, we have greater solutes, the green dots, outside the cell than inside the cell. And again, there's more water inside the cell. We can't pull in those solutes into the cell. There's no mechanism for that because the semi-permeable membrane will not allow it. So we can send water outside of the cell to equalize the solute concentration, and when we do that, the cell shrinks. So eating salty food, such as a cup of noodles, it causes sodium ions to spread through the blood and then the extracellular fluid. And so what's happening is more concentration of solutes outside the cell. We get osmotic pressure that's building up. It starts to draw water from inside the cell to the outside of the cell. So what can we do? Well, you get thirsty. Have you ever had something really salty and then you get thirsty? I'm drinking this giant water with my cup of noodles. It helps to restore the body to its normal state. What are the physiological mechanisms that allow us to detect that osmotic pressure, right? That, allows us to say, I think I'm thirsty because I ate something really salty, right? There are specialized receptors hanging out around the third ventricle, where that cerebrospinal fluid is located. And also we have the organum vasculosum laminae terminalis, and a subfornicular organ. They have receptors that detect osmotic pressure like that, and the sodium content in the blood as well. And if they did not regulate the sodium content in the blood, we would die. So they're very, very important. We also have receptors in the periphery, including in the stomach and the digestive tract, that maintain the intracellular and extracellular balance and osmotic pressure.